The show is back. Thanks so much for coming on my show, Sam.
Yeah, thank you for having me.
Ladies and gentlemen of my audience, Sam Mundy is a mathematician. He's a number theorist. He overlapped with me, I guess, in my final year. That was your first year in the math PhD program at Columbia, right?
It was actually 1 year separate from that. I stayed with you as a prospective grad student. I stayed at your place as a prospective grad student as the year you were graduating.
Okay.
Through that, but we never overlapped at Columbia, actually.
Oh, we never actually overlapped, but nevertheless, in our conversations, I was convinced you were well on your way, because we actually have something similar in our background, that we both went to the Promise program, right? And I think I remember back then, which must have been in spring of 2015, that you impressed me with your knowledge of number theory and your sense of what it was that you wanted to do, which is a rare thing for incoming grad students.
Thank you.
But now you have your PhD and you are an NSF postdoc at Princeton, right?
That's right. That's right.
Okay. Well, I saw your post about your paper that you finally finished. I guess it's an extension of your thesis. Is that?
That's right. That's right. Yeah.
Your paper, Eisenstein series for G2 and the symmetric cube Bloch-Kato conjecture.
Yeah.
Kato or Kato?
Kato.
Kato. Yeah. Okay.
Yeah.
You see, I'm not in this field.
It's okay. It's a Japanese name.
Yeah. Well, sometimes even with it depends, even European names, somehow we get into a pattern of saying it a certain way, and it's not necessarily the way that. Anyway, so I saw this and I said, you want to talk about this on my show? And you agreed, which is a great thing, because this we haven't had a podcast in a while. Hard to get people to agree to come on and be subject to my grilling, but also I think it's a good way. Hopefully, we'll promote your good work here.
Possibly.
Yeah. But I'm also very. Yeah, I'm very curious, even though, so I'm not an expert, but we'll see what I can learn here, because, number theory, like you, it's my first love from going to Promise. And although I didn't end up working in that field, not exactly, I guess I still am interested in certain questions there, always maintain my curiosity. But how about, before we dive into some serious hard math, want to tell us a bit about your background. How did you come to this?
To this, you mean
type
like
of math?
This type of math? I guess it was also through the Promise program. So for those who don't know, the Promise program is a 6-week intensive number theory camp during the summer. It happens every year. It's been a little weird with COVID, but it still is happening every year in some form or another. And so in this setting, what one does, so there are two tiers of students in some sense. There's the first years and the second years, for the most part. In the first years, the students who have only been there for their first time will essentially learn a 6-week course, and like very intensive, college level course in number theory. And these are high school students, so they're learning number theory as high schoolers.
It's a lot more. I would say it's actually a lot more than that, because
it's definitely a lot more than that. Yeah.
It's not even just that you are taking a college course in number theory. It is exactly a mathematical boot camp where you are building it all up on your own.
Right. This is what I was about to say. Students. Exactly. You're supposed to, guided by these problem sets that you get every day, or at least every weekday. You sort of build the entire ground of elementary number theory on your own, or talking to other students, but yeah, essentially on your own. And that's what it is. And so I I liked the things that I learned for myself at this number 3 program.
It's an absolutely wonderful training for mathematicians that is even something that is not there at the university level. It's something very different from a university course. I think I already talked a little bit about the program with Josh Zielinski. Did you ever meet him? Do you know?
I didn't watch the one with Josh Zielinski. I watched the one with Jeff.
Right. Well, I've been trying to get Glenn Stevens on the program.
Oh, yeah?
He said he would, but he's a very busy man, I guess.
He's extremely busy. Yeah. Well, hopefully you can get him, but yeah, we'll see.
I'd love to get Henry Cohn too. But
oh, yeah.
Did you? I'm just curious. What was your exposure to math prior to Promise?
Yeah. So prior to Promise, it was just whatever math I was learning in school. I guess I did. This middle school program, Math Counts. It's like a competition.
That's right. I remember participating in this competition, actually. Yeah.
I did some of that in middle school, but I wasn't that into it somehow.
Where'd you grow up, by the way?
I grew up in Albuquerque, New Mexico for the most part.
Oh, yeah. That's right. I remember. Okay, yeah. Now I remember.
I was born near Boston, but then moved to Albuquerque when I was a kid.
Near Boston? Where? That's my neck of the woods.
Oh, yeah. Is that where you are now, or?
Yeah. I'm in Framingham. Okay.
Oh, cool. Yeah. So I lived in Wellesley for a while.
Uh-huh.
When I was little. Yeah. Anyway, yeah. So cool. So right before that, it was just it was I was always into math since I was little. So like when I was in high school, I would take more advanced math courses than typically students of my year would.
So you went ahead.
I went ahead. Yeah, I was 3 years-ish ahead.
3 years ahead?
Yeah, I think I took calculus as a freshman in high school or something.
That's pretty good. I mean, I think that's something that probably should be more available to people if they can make it. I'm not the biggest proponent of actually skipping people ahead grades and putting them entirely with people who are not their age. But there are people who are ready to take on a lot of math, and if you can give it to them, that was just not there.
Right. So that was probably available because of my Montessori school upbringing when I was little.
There it is. There it is.
Yeah.
Okay.
So I guess that's the answer you're looking for, more or less. Yeah.
Okay, that helps. It make some sense to me. I mean, I'm just curious about this because some people come to Promise having been exposed to certain things or certain things in math, and I just, for me, it was such a revelation because I had never. I mean, I was in this regular class, but I was just so bored, and then someone showed me this application to Promise and that the problems in this application, I'd never even considered going to a math camp, but I couldn't help myself from working on these problems. I just had to be part of this. And then to see that there was a world where people do math and what sorts of questions that they, it was all totally new to me.
That's interesting because the application is not what drew me in. So I was definitely one of those kids where, your parents made you go to Promise. I wasn't
really
that into it. I wasn't that into it at first. And then when I got there, I was like, this math is unlike anything I've ever seen. Nobody's told me how to do a proof correctly before in any sense of the word correct, right? Nobody, except maybe in geometry or something, but that's different, right? So. And
what year was your first year at Promise?
I was 15 years old. That was in 2008. I was 16 years old then. So yeah.
Okay, I was 16.
2008.
16. My first year in 2003. 03,
okay,
04 is when I was there. And so, is it a direct shot? So how many summers were you at Promise?
So as a student, I was only there once. And then as a counselor, I returned as a counselor as an undergraduate for 3 more years.
Uh-huh.
Yeah. That was 13 through 15.
Where'd you go to college?
I went to the University of New Mexico, just nearby home.
Uh-huh. How is the University of New Mexico? I guess I don't, maybe not all of it, or anything you want to say about it. I don't know anything.
Yeah, I personally had a good experience. There's exactly one number theorist there. His name is Alexander Bouillon. And he was a wonderful mentor. He was just absolutely wonderful to have around and talk to, and go to his classes and so on.
I think I've seen that name. Brilliant, is that what you said?
No, Bouillon.
Bouillon. Oh.
B-U-I-U-M. Bouillon. Yeah, Alexander Bouillon. Yeah.
Oh, okay. I don't know that. But you knew you were going to do math from after Promise. Is that right?
Yeah, more or less, maybe a little before Promise. So I guess when I was in, so the year in high school before Promise, I was really into, like, you know, I think I told my teacher I didn't want to go to class anymore because I wanted to figure out everything on my own. And wow. he actually let me do that. And I was like, okay, just as long as you write up a report, you can have your final be like, you write up a report on what you've learned.
In what area of math was this?
It was just calculus too. I just wanted to sort of figure out, you know, whatever integrals of trig functions and things like this on my own or something. And so, you know, I was very into doing, you know, these kinds of things on my own. And just trying to figure out for myself, and that plays into the whole Promise thing, where, you know, figure it out for yourself, more or less.
Well, I give you a lot of credit for that. That's an impressive attitude to take as a high school, and even before Promise. On the other hand, I wonder, you know, someone at that stage, I think needs a lot of guidance, but I mean, and figure out, and certain things where it's, you know, it can be made a lot more efficient if you were guided in some directions.
Exactly. Yeah, I completely agree with this, because I think, you know, having a lack of guidance at that point in my life with mathematics was definitely, well, like I said, you know, the stuff I saw at Promise was unlike anything I've ever seen at that point. And, you know, that's more or less how people do math in some sense. And, you know, without knowing how to really do math, and going and, you know, trying to spend the last quarter of, you know, 10th grade in high school on some math that you don't really know how to do is a little iffy, but, you know, I guess it worked out. So
yeah, did work out. And so you kept with, you knew you were going, not just you were going to do math, but maybe after Promise you were going to do number theory.
Right. Well, I didn't really know immediately after Promise that I wanted to do number theory, but it, you know, as I thought about it more, it became more clear. Like, for me, number theory is that one area. The thing I like most about number theory is that it takes in so much other mathematics and combines it in interesting ways and outputs actually real results from it. So, you know, as I learned that this was the case, you know,
it's funny that you say, by the way, I just want to point, when you say it outputs real results, you know,
I'm not putting down other fields at all. No, don't get me wrong, and don't misinterpret that.
That's actually maybe another interpretation of the term real than even I was thinking, as ascribing a significance. I was only referring to maybe the concreteness. You know, some people have talk about number theory as though it's abstract in the sense that it doesn't, it's not applied mathematics, or it's not, except that it is, it actually is today. In the field of cryptography and computation, but there are some people who, you know, Gauss praised number theory as the queen of the sciences, and you know, when Hardy spoke of number theory, he thought of it as something that was totally not related to the real world. But I think maybe what you meant just now, is it possible you meant it's very concrete? The results seem tangible somehow to you?
I guess really what I meant is that it outputs results from this weird combination of all sorts of other maths successfully. Just that it does it successfully, right? But then, what do I mean by successfully, right? So, yeah.
It's just that, even in the field in which I work, if you have a solution to an equation or getting some it seems like a very concrete thing to me. And then I try to say something to a lay person about, they think just all math, it's like having defined, what is to them a manifold. It's like a completely abstract thing. So what am I even talking about? But I don't know. It's very real to me at some level.
Right. And yeah, I also agree with this coming from number theory that it's real in that sense as well. Yeah.
Okay.
It's much less abstraction than it has to be much less abstract than, say, something like algebraic geometry in the 1960s, because it's really an application of a lot of other mathematics. Like you have to get specific, right, to get.
Yeah. So I think we are somehow on the same, even if we can't totally specify what do we mean concrete. Yeah. I'm with you with like that field is abstract. And here, this number theory about L functions and their order, the points on curves. That's concrete.
Yeah, it's concrete, but it's still very mysterious.
Okay, yeah. Well, lots of good questions to ask.
Exactly.
So I'm wondering, did you have any further? Was there anything in your education that was as much of a revelation in your thinking, or that directed you on the level of promise, after that?
Anything on the same level as promise? Probably not. That's a good question, though. Yeah, I don't. Promise sort of got everything started in the right way for me, right? So. No, nothing that was, yeah. I mean, everything was sort of more gradual after that. So,
I see. For me, I tried to learn a lot of different math in college, and it ended up having to make some decisions about what is good math and what I wanted to pursue. I've had some changes in my thinking over time. Different where I went to grad school, who would be my advisor, what math would I ultimately pursue. Somehow these were all, I got lost, sidetracked from maybe my original goals. But okay, so now
but maybe I have a different answer to this question, sort of like definitely a formative point in my development as a mathematician was very recent, when I really felt like I was going from just learning to actually learning and doing research, right?
Mm-hmm.
Actually getting into doing research, I think, took me a long time, more than it takes a lot of people, I think, actually. So I think really it wasn't really until, I don't feel like it was really until my fourth year of grad school where I was really making any progress in the research direction.
Yeah, that can
actually
happen. That's
writing down new math, right? Sort of, yeah.
So if you took your oral exam in your second year, right?
Yeah.
And that the third year, you're presumably working on research, but it's hard to get somewhere. I think I had this same experience.
My third year was also weird in the sense that I had some like serious health problems then, and I needed to take care of those, and so not much math got done in my third year. There was a lot of losing weight in my third year.
Well, Sam, I do want to, because this is something I'm very impressed with. Because I when I first met you, have lost, right?
Yes. I lost about 100 pounds in my third year. Gained some of it back, but a minor amount. Yeah.
How did you do it?
Yeah, that's a very good question. So, well, the thing that triggered the whole thing was like, I went to the doctor for the first time since I moved out of my house in New Mexico, and the doctor told me that I was pre-diabetic. Like, we did blood tests, and there was this news, and I thought that was shocking, especially since in my family, there are people with diabetes, and I know how much that, screws with their life and so on. So I was like, I really don't want to go down this road. So luckily I had a friend I asked my friend to help me, like, check in on me in irregular periods, and asked me if I'm losing weight or whatever. And she was like, yeah, I'll do that, but you need to actually write down some, very explicit goals that you want to achieve that are along the way to just losing weight and not being pre-diabetic anymore, that are tangible and within reach. And so I did that, and sort of I used like apps on my phone to keep track of, the concrete goals that I set for myself, and went on that for like about a year.
But I guess I mean, okay, so that's good psychologically, but how much of it was you changed your diet, or you changed your exercise, or both?
Both, but mostly diet.
I see.
Yeah, this was also around the time where I got really into walking, like in general. So you might know that I am a big fan of walking.
You walked from New York City to Boston.
Yes,
I remember seeing your a post about that.
That was the summer after I lost all that weight. So.
I see. So you had already done a lot of that work, and it's the culminate, like you decided to go on an adventure or give yourself a challenge.
Yeah, it was just something, I was like, I really enjoy the walking part of this endeavor, and let's actually go somewhere when we do it. Yeah. So
and you did
that was really the idea.
You did this alone, and
I did this alone, yeah.
And how did you walk? Walking along the highway? How did you?
No, never. So I never walked along the interstate, because probably that's illegal or something, and you just shouldn't do that. In any case, so I picked a path that was sort of very well populated, so that there would be roads with sidewalks or otherwise, breakdown lanes or whatever, all along the way, almost all along the way. At some points you had to do some iffy things, but for the most part it was okay.
And you what would you with a sack, and did
you?
Yeah,
with a backpack, with a camping backpack essentially.
But wait, did you camp? Okay,
no,
good.
I didn't.
You did.
Yeah.
Okay, you stayed in place, but okay, and you did it just listening to music. This is a remarkably disciplined. I don't know, like a pilgrimage, like a thing a monk does, or something.
It was just something unusual that I felt like doing, so I did it.
And you still felt like doing it, I don't know, halfway through. How was?
Yeah, no. I mean, the scariest part was just at the very beginning, where I didn't really know what was ahead, and then after so it took a total of 24 days. After the fourth or fifth day, it was like, yeah, this is definitely the thing I want to be doing. So I did it.
Well, I've walked maybe in Manhattan. I did a lot of walking when I was at Columbia.
Yeah.
But I don't know if I would do the same thing, but I am very impressed with it. It shows me you're a serious, disciplined person ready to take on some challenges.
Well, I don't know how disciplined I felt like it was a break from everything, sort of. It was a weird way to take a vacation somehow.
Interesting.
The discipline came in blogging about it every day. That was the most disciplined thing about it, I think. I have a blog about it, and I just actually writing the post every night was the most discipline I had on that trip. But otherwise, it was just sort of relaxing in its own weird way.
I don't have the discipline to go on a diet. I like to eat, and with my own weight.
I don't know that I have the discipline to do that anymore. Right. So
I don't know, since I came to Framingham, I was out of shape, and been going to the gym, because that's the way I hope to do things, because I somehow cannot be disciplined about I already think I eat decent, but to do it in a way that you're, I don't know, getting under some percentage body fat. But I have managed to convert. I'm the same weight that I was, but I've converted 15 pounds of fat to muscle.
Oh, congratulations.
With my lifting.
Very good.
Well, I don't know if I'll ever have totally defined anything, in my torso, but we'll see. But they have a wonderful machine at the gym, a scale that with some electrodes, so it measures your body fat and skeletal muscle.
That's how you know that.
Yeah. But you see, because of this, I just during COVID, I qualified for the, as having a health condition to get the vaccine ultimately like 2 weeks early as being obese.
I see.
because by my BMI, because I put on muscle.
Right. Yeah.
I'm built like a running back now. Whatever. Anyway, I'm not obese. Yeah. Anyway, so I'm very impressed by that endeavor. Besides your mathematics, I know you also have a blog. I think I remember you talking about your love of metal music, which I guess I can't get behind.
I tried to have a blog about metal music over the pandemic, and then I had to write my thesis. I still want to go back to it, but I'm so busy.
God, I'll never understand that, but I probably can't. I'm not going to win over anybody talking about the music I don't like. Okay, so let's talk about some number theory. By the way, do you think of this? Are you like an analytic number theorist, an algebraic number theorist?
I'm not an analytic number theorist. I don't know if you can call me an algebraic number theorist. On the other hand, I don't know. I would just say I'm a number theorist.
I see, because you know what, in this title of your paper, I assumed that and who you worked with, or I thought that you were an analytic number theorist. But looking through this long paper, I did not see many inequalities.
No, that's right. No, I mean, what I always saw myself as more of an algebraic number theorist after a certain point, like in undergrad, like it became clear that I was more on the algebraic side than I was on the analytic side. Of course, when you're dealing with automorphic forms, you need both. So.
Right. Okay, so here is my challenge, which I've given to a couple of my guests. How do you explain what you do, if you ever try to do this at all, to a lay person? I'm sure at some point this comes up for you.
Right. So this is very hard, but I can try my best. I have made this attempt before. So the thing I would say is I would babble about the Langlands program in some way, that there's a correspondence or something. Maybe that's not the best way
babble away. People are listening.
Okay, I can give it a shot. So I always feel like you have to avoid jargon in some way, and it's very hard. Okay, let me give it a shot.
This is very. Let me. The thing that you study, I've tried to understand at least on some level. I know some of. I think I'm better with the 19th century. This theory of modular forms is now over 200 years old. Right? People have been studying
over 200, but pretty close. Yeah.
I'd say it goes back, to Gauss, and you can see even the theory of elliptic integrals is actually pre-Gauss.
Sure. Okay.
Sure. And Gauss knew a lot of the identities and had the theory of modular forms in his work already in the early 1800s. So very smart people have been working in this specific area of math very intensively, not without interruption for a long time. So it's very hard to for someone coming at it with nothing. It's a very hard to say. It's all jargon at this point.
Right. Of course.
To say what is the point of this very detailed study, but I don't know. It's try to say something if you can.
Yeah. So, well, I guess, maybe one way to start is by answering the question, more or less, what is number theory? And the way I would answer that, so let me try to answer that first, and then we can see if I can build a layman explanation of my work on top of that. So number theory, for the lay people who are watching this, historically it's the study of whole numbers, right? So what is interesting about whole numbers? Well, there's a fact that, if I give you any positive whole number like 12, I can always factor it into prime numbers. And moreover, up to reordering those factors, that factorization is unique in the sense that, I can't build it out of any other, chosen set of prime numbers. So
a nice fact.
Yes, it's called the unique prime factorization theorem. But in the early, maybe the mid 1800s, there were various reasons mathematicians wanted to think about not just whole numbers, but number systems that are like the whole numbers, but aren't the whole numbers. So an example of such a number system would be what are called the Gaussian integers, where you take a plus bi, where I is, the usual complex, imaginary unit, the square root of -1, and a and b are integers. You just consider complex numbers whose entries are integers. And then you can add them, you can multiply them, you can subtract them. And even further, you have a unique prime factorization for this number system. So mathematicians knew even earlier than the mid 1800s that this number system has, this property that if I give you these are called Gaussian integers. If I give you any Gaussian integer, there's essentially a unique way to factor it into prime Gaussian integers. And then there's this interesting phenomenon that happens that some of these prime Gaussian integers are also prime integers. Like, inside of the Gaussian integers, you have a plus 0i, where a is an integer, so the integers sit inside the Gaussian integers.
Can you say why or what problem motivated that study? I'm just imagining this layperson starting to think to himself, here goes a mathematician just worrying about abstract concerns for its own, why should we like a unique prime factorization in the Gaussian integers? Or
right. So you can use this fact that every Gaussian integer factors uniquely into prime Gaussian integers to study the integers themselves. So there's a theorem due to Fermat that says, if I give you any prime number, and if I divide that prime number by 4, I get a remainder of 1. If that happens, then you know that prime number is a sum of two squares, two perfect squares. So you say something about something that we already wanted to study, namely the integers. You say something about the integers using these Gaussian integers, and how do you do that? Well, you have to prove it, but the right proof of this fact actually goes through the Gaussian integers, the right in some sense. The easiest proof of this fact goes through prime factorization of the Gaussian integers. And that's just because if I take a plus bi and I multiply it by a minus bi, I get a squared plus b squared. And that's sort of more or less where you see the sum of two squares coming.
Okay, let's just say that the layperson is satisfied with that.
Okay, hopefully.
I think
I don't know.
that, and I think what you're in this mid 1800s, you're talking, Lemay tried to prove Fermat's last theorem, and
Yes.
Kronecker showed him he had an error because there isn't
right.
prime factorization.
Yeah. So exactly. So going back to this mid 1800s stuff. So there are many ways you can extend the integers, like I did by considering Gaussian integers. There are other number systems that contain the integers inside themselves. And in fact, not all of them have this property. In fact, very often they don't have the property that there's unique prime factorization. And and what happens is there's sort of some defect that number theorists eventually figured out how to measure in a precise way to having unique prime factorization. This is called the class number. But anyway, the study of such things takes you through this world of algebra and this world eventually of analysis to really get back at, trying to study things like prime factorization and things like this. and Fermat's last theorem, because Fermat's last theorem, as you pointed out, was almost solved except for this error that, you know, if all of these number systems, they're called number fields, if all of these number systems or number fields, whatever you want, had unique prime factorization, then Lemay would have proved Fermat's last theorem. But unfortunately, or fortunately, because it's actually an interesting defect, this was not the case.
And where are we? You know, I'm just thinking already with this notion of the class number and this thing called the class group, quantifying that defect, that gives you stuff that, you know, knowledge of the size of the class group for different number fields. There's still so many open questions, and the structure of that group. You're already given enough for a mathematician to spend a whole career, or a whole, there's a whole
many
industry.
Careers. Yeah.
And lots of good stuff. Getting at that will bring in even more structure and stuff that's related to your work, right?
Yeah, so yeah, maybe I can start to say some things about my work. So
yeah, okay, so maybe we're beyond,
yeah.
I maybe the layman is not, we're beyond that point. Now talk to a mathematical audience that,
okay.
You know, it's not in your field though.
Okay. It was not in my field. Okay. So
because that's me, I guess, or
right.
I know maybe a little bit.
Yeah. So then you know that there is this thing called the Langlands correspondence, where if you want to study the symmetry group of these number fields, namely the absolute Galois group of Q, as it is called, then if you want to study the structure of this group, and hence the structure of all number fields at once, then you need to understand how this group is going to act on various vector spaces with certain structure. And these group actions, this Galois group acting on these vector spaces, I mean, those are called Galois representations. And, you know, I'm very interested in studying these Galois representations for themselves. But how would you do that? And how would you even construct, you know, an interesting Galois representation? Well, you would use this Langlands correspondence that I've been referring to, and you would start with something much more analytic called an automorphic form. Automorphic form at its core is an analytic object, or a harmonic analytic object in some sense. And
I think I might have to stop you.
Okay.
Because you're using maybe a bunch of terms.
Okay.
You're skipping already to something called an automorphic form, or an automorphic representation, even before talking about something called the modular form.
Okay. So do you want me to start with modular forms then?
Well,
what do you want me to say?
Well, what is the, I was already skeptical of this idea of talking about it. To me, this, I've heard a lot about this Langlands picture over the years, that there's like a philosophy of sort of putting together all of mathematics. This thing is related to this thing and is related to the, and of course that may well be, and be very interesting to some people. I have to say though, my own preference is to think of the purpose of mathematics as not putting it all together in some nice synthesis, but to answer specific questions. If you know, if you could tell me, my goal is to understand this, you know, here's a concrete question, it has an answer, I don't know the answer, what is the answer to that? And then of course we'll have to look at it in any way we can and make the appropriate distinctions. I would love if you could phrase your interest that way, instead of trying to put it into the Langlands picture.
No, so I'm not trying to use Langlands as a motivation here. I'm trying to use Langlands as, this is the thing, this correspondence is what I use to actually study these Galois representations.
Okay, so
whether I can say anything more concrete than Galois representation is another question. So I want to study these Galois representations, and how do I study them? I study them with automorphic forms.
Okay, there's some, as I take it, I get the idea, maybe people, undergraduates who take an algebra class will know that there's some symmetry in the roots of polynomials when people are trying to solve, how could they express the roots of polynomials? There's a group that permutes the roots, and something about that structure of that group tells you how to solve for those roots. You are thinking of all of those groups all at once.
Right.
But in one object that's very mysterious. We'll probably have to specialize when we actually say anything concrete into the number fields generated by the roots of any particular polynomial. But it turns out, and then in this theory of how do you study that group through its representation theory, somehow the numerics or the things attached to that are also attached to these analytical objects that you're calling automorphic forms, and
I don't expect to believe that anybody listening knows what an automorphic form is. I don't want them to, try to look up the definition or anything, because it's not going to do you any good.
Yeah, it didn't do me much good. I guess I think I know what a modular form is.
Right. So maybe I can think about. So the paper that we mentioned at the beginning of this conversation is about modular forms. It's really about the Galois representations attached to modular forms via this correspondence that I've been calling the Langlands correspondence.
Right. So by the way, I noticed a couple of key words. If you try to read even your abstract, it's just begin. Let F be a cuspidal eigenform
right away. Yeah.
And let fix a prime P and let rho F be the Galois representation attached. So I came up with a couple of these key cuspidal eigenforms. So maybe that has the idea of both modular forms and these things that are very mysterious but all important in this theory, the Hecke operators.
Yes.
Galois representation, you have the L series attached to that. This Bloch-Kato conjecture, maybe you could help describe to me what that is. I sort of, this is a generalization of the Birch and Swinnerton-Dyer conjecture.
Mm-hmm.
Right. Oh, okay. And then you have the Eisenstein series. You have this thing G2 in your title.
Yes.
Which we may want to, maybe you will tell us a little bit about, because I'm aware of this thing G2 from the classification of compact simple Lie groups, although I understand it as its root system, which was allowed by this theorem, but I don't think I've ever worked or looked at the group G2.
Yeah, I also understand G2 by its root system, by the way.
Well, yeah, so you have to start there, but also I see you also seem to understand as a group these alternating trilinear forms and
which usually I understand it by its root system. On the Galois side, I actually understand it some other way. Okay.
The symmetric cube. You have this. There's this discussion of étale and crystalline cohomology. Those are things I don't know what they are. Now you're really getting to something.
No, crystalline. I don't say anything about étale or crystalline cohomology in this paper, but okay.
Are you sure? Because
I use the word crystalline in a different but related way. I don't think I ever say étale.
Well, maybe you might need it for the statement of the or at least of the conjecture in general.
The conjecture in general, you need crystallinity, but not in the sense of crystalline cohomology.
Okay.
Anyway,
you talk about this thing called the Selmer group, which I don't know what that is, or and there's some deformation theory happening, which I'd love to know more about what that is. And you also mention Arthur's conjectures, and I don't know what those are. Where do you want? I do want. So I don't know if this is the best way. You don't have a blackboard. This isn't a talk. It's not a job talk. But anything you can say now. I have lots of there's just things I want to know about and see if you can help me to understand. Now we're at the point where it's sort of just my curiosity, my questions about this subject. Just starting out with the basic project of what you're trying to do. I feel like I understand the project of the Birch and Swinnerton-Dyer conjecture.
Okay.
Which is not finished at this point, right? It is known only in some special cases. Which can you explain what that is, and maybe what the Bloch-Kato, how this extends it?
Right. So the Birch and Swinnerton-Dyer conjecture is about elliptic curves. They're about this object called elliptic curves. I don't know, maybe I can refer the viewers to the conversation you had with Jeff.
It's true. You know what? I went back and watched a little bit of that conversation, which we recorded about a year ago. And I know we're covering some similar ground, but I hope to cover a few different things.
I know, this would be different than only that, yeah.
Let's say at this point, because I think I know what an elliptic curve is.
Okay.
So now say you're just talking to me here.
Okay. Yeah. Okay. Fine. I'm just talking to you. So, if you have an elliptic curve, then by Wiles and by Broy, Conrad, Diamond, Taylor, you can, and of course you should say Wiles and Taylor Wiles, I suppose, not just Wiles. That's wrong. Taylor made contributions to that paper as well. So okay. Anyway, so if you have an elliptic curve, then there is a modular form such that the L functions of both of these objects agree. There's a connection between this elliptic curve and this modular form, and it's, one way to see it is through its L function. Another way to see it is through the associated Galois representations. So these both have Galois representations attached to them. And
it is by the way, so maybe we'll get to this a little bit later, but it is a confusion. This is a point of the theory I do not know well or very well at all. How do you start from a modular? What is the Galois representation attached to a modular form? This thing in the second or third sentence of your abstract is a part of the theory. I don't know quite.
So can I explain that a little bit?
Oh, if you want to take that on now, sure.
Yeah, sure. Let me do that. So a modular form has a Fourier expansion. So, and if you divide by A1, the first term of that Fourier expansion, so really I'm talking about a cusp form, so there's no A0 here. So a modular form starts with, A1 plus A2, or A1 times Q plus A2 Q squared plus A3 Q cubed, and so on. Okay, so you get the sequence of integers, the Fourier coefficients attached to this modular form. And then on the other hand, so what does it mean to attach a Galois representation to a modular form? Well, it means that there's some Galois representation such that if I take any prime number p and I look at what's called the Frobenius at p, so this defines some conjugacy class in the Galois group. What the Frobenius does is okay, so if you looked at if you just took some number field and you looked at that number field mod p, or the ring of integers in that number field mod p, you would get this p power operation on it, which is a field automorphism because you divide it out by p, right? So this is more or less Fermat's little theorem.
So whenever you have an extension of number fields, you have this Galois. I understand the Galois group of that extension, right, which permutes the elements of the bigger field and fixes the lower field. And so you can also think of that as dividing. You can mod out by, primes. And there's
so primes give you elements of that Galois group is what I'm trying to say, and those are called the Frobenius elements. And what they do is they raise to the pth power up to p, up to modding out by p.
Mm-hmm.
So so these are called Frobenius elements. and they give you elements of the Galois group, and actually they're dense. You know, the Galois group, the absolute Galois group of Q is a topological group. It's a profinite group, in fact, and these are dense in that group.
Okay, well, that's very hard for me to get.
It's a weird, because it's a weird topology, and you know, whatever. But anyway, what that means is if you know what all the Frobenius elements do, then you know what everything does, because this is a continuous action. So if you know, so it's like, you imagine you have a continuous function, and you know, like on the real line, and you know its values at all the rational numbers, then you know its values everywhere. It's the same kind of thing. Right. So what you can ask for is the trace of the operator given by Frobenius on your vector space. Frobenius at P gives you an operator on a vector space, since the Galois group is acting on that vector space. And you can ask for the trace of that operator. Right. So I can ask for the trace of that operator, and I demand that the trace is equal to the p Fourier coefficient of my modular form. And it's some miracle that such representations actually exist.
Yeah. So that's the part of it that I I can imagine, if you have some representation of the group, and you can take the trace of Frobenius and give yourself a sequence of coefficients. It's that construction. It's the taking of the modular form and knowing that there's some representation with that. That's the construction that I get very confused about.
Right. This goes through the theory of the Jacobian of the modular curve, right? So, right. So you need
and by the way, and the interpretation of these Hecke operators on that object. That's where I start to get a bit lost, because these wonderful Hecke operators, they make sense to me as operators on lattices, on functions defined on lattices. And then these things seem to get multiple interpretations in different places. Right. So I actually was sort of hoping you could speak to some of that, because I don't know, if you start working with these other groups, do they, I know what it means out of these Hecke operators, where we're talking about congruent subgroups of but not these other groups that seem to come up in your work.
Right. So the for these other groups, the Hecke operators are really interpreted on the group as like, how do I say this? Well, I don't know what question I should try to answer right now.
It's a little bit, it's too, okay, I'll grant that it's too much. Is there a way you can, just because is there any short way of explaining how you get this Galois representation attached to a certain modular form? Like which what does it go through? I don't understand the absolute Galois. Any representation, it's factoring through some number field, right?
No, it's actually not. It's because these vector spaces are really like p-adic vector spaces, and so they're also their topology is more compatible with the topology on the Galois group than say the complex numbers are. So what you were saying is what's called an Artin representation. If it has finite image, like if it really factors through a number field, then it's called an Artin representation. But these Galois representations attached to modular forms are not Artin representations. They have infinite image.
Okay. All right. But what can you say about, but it has to be some particular thing attached to a particular modular form. And by the way, I'm also sorry to add more questions to the issue, but I have more of a sense of how you do it in weight 2, because in weight 2, that is that's like a holomorphic differential form. I understand how to integrate that thing, but when you're talking about weight K in general, I'm much more confused about that.
Yeah, so I mean, let me preface this by saying I never use the construction of these things in my work. I use that they exist and they have this property that the trace of Frobenius is equal to the Fourier coefficient. Right? I never need to use the construction. So maybe I'm not even a good person to ask about the construction because of this. But,
I see. Okay. I mean, I don't
need to use the construction. I need to use the properties of this rather than the actual construction.
I see. I'm just trying to understand the objects at play in this Bloch-Kato because, okay, so I understand this, the statement of Birch and Swinnerton-Dyer. And let me see if we agree that the idea there is you have an elliptic curve, which is some equation that, some cubic, and you can study if an elliptic curve over the rational numbers, say, and you can consider that mod p and count the number of solutions mod p for every prime. And this is some nice set of numbers associated to that elliptic curve, and we have nice bounds on those numbers, but they might vary particularly. And you can attach this L function to that thing, and somehow Birch and Swinnerton-Dyer, even well before the modularity was proven, they looked at how the numerical defect divided by p. And they summed that and looked at how that grew.
Yes.
Up to
But they used modular forms to do that. They only looked at the case of elliptic curves they already knew were modular for other reasons. They used special cases of modularity, actually.
Oh, even
yeah. So they all their computations were done on modular forms, actually.
But couldn't you? Oh, okay. I just saw this nice table in Knapp's book in his introduction, which sort of shows you the beginning, the origins of how someone might have conjectured that, the order of the zero of this thing, which is of a function which isn't even initially defined, where at the point where they're talking about, it should be equal to the rank of this elliptic curve over Q. Which is such a tantalizing, if that's true, boy,
and of course
that's amazing.
Because they knew these elliptic curves were modular to start with, they had access to the L function of the modular form, which they did know was defined at that point.
I see. Okay. Well, okay, so I think I understand the statement there of Birch and Swinnerton-Dyer, and as far as it's been proven in rank 0 and 1,
more or less. I think there's some asterisks there, but yes.
Oh, there's some
something like this.
But man, I would love to see that. How do you take to show that you have an L function that vanishes to higher order and start constructing points that have non-zero height, but are not, that are independent of each other.
Right. So the kinds of things that I work on could get at a question like that for higher order, but not construct all of those points, essentially.
Yeah, that's what I... So would you say that the thing that you are doing is somehow a little bit analogous to that that construction, that thing that I was just saying, but in this other setting, you are looking at you're looking at now some L function.
Yeah, I'm looking at I have an L function. That's right, and I'm looking at its order of vanishing.
Yeah, but the L function, so you haven't started with an elliptic curve. You're starting with an L function attached to a modular form.
Or really, I'm starting with an L function attached to a Galois representation.
Okay, and now
okay. So let me say something here.
Okay.
So if you start with an L function attached to a modular form, how are you going to build it? You're going to use the Fourier coefficients, right? This is the definition of an L function attached to a modular form is like an over n to the s, where an is the Fourier coefficient.
Yep.
And if it's an eigenform, then it factors into an Euler product, just like the Riemann zeta function does, and so on. But In any case,
yeah, this is actually a wonderful part. Yeah, if it is a simultaneous eigenfunction of all the Hecke operators, and that's what means that ostensibly of these functions that have all these wonderful symmetry properties on the upper half plane, they could they have a Fourier series, so they have you plug in, they have some coefficients. But actually, if it's these Hecke operators, if they're not simultaneous eigenfunctions of those, that's what makes them have nice coefficients.
Exactly. And coefficients that are determined at every prime instead of every integer. Right. You could just look locally at each prime and get all the information you want. And similarly, if you have the Galois representation, you could build the L function out of the Galois representation attached to the modular form, because the Galois representation, as I explained, already knows the Fourier coefficients of that modular form.
Right, and so it's that one extra, this component of the theory where you go from this Hecke operators, how they act on the Jacobian, and what they end up having to do with those Frobenius elements of the Galois representation. That's the part that I find very difficult. I don't know that I can explain it in any satisfactory way here, but okay. I won't.
Some very a priori very weird construction of Shimura, right?
That's who did this.
Shimura, essentially, yeah.
By the way, what are the references? Do you have, how did you learn this subject?
Right.
That's a quick aside.
That's a good question. I guess Diamond and Sherman is a nice place to look.
Yeah, that's a nice book that I haven't spent
just for modular forms. Yeah, that's probably my answer is Diamond and Sherman. I also did read Knapp's book. I somehow like Diamond and Sherman a little better, but Knapp is different, but it's also good in different ways.
Yeah, Knapp is very concrete and
yes.
Makes a lot of sense to me, and it's very surprising in a book that starts out nice and simple. It brings you up to this Eichler-Shimura theory, but it does get a little bit vague, or a little bit they're relying on some other thing. That's why
they need to rely on some algebraic geometry over fields that aren't algebraically closed in order to get it to really make everything precise. So they have to align something there.
Yeah, so some questions as to why some of these things are given by equations with rational coefficients, or why do these that's why it's very confusing to me. Maybe I will spend some more time with the Diamond and Sherman to understand this part of the theory. Okay, I mean maybe that book could probably. I was looking at it today, by the way, so that could probably get people pretty far. I like, did you see, I don't know if I had any business doing this, but I gave the reviews of some books on elliptic curves on my channel.
Oh, no, I didn't see that.
Well, we can see what you think of my opinion of these books. I really like this book by McKean and Mole on elliptic curves.
I don't know that book, actually. No.
Which covers the history, starting with elliptic integrals.
Okay.
And talks about, probably this function k squared in Jacobi's parameterization of these elliptic integrals was the first modular function.
I see what you're saying. Yeah.
That parameter, it is a modulus of these
right.
Curves. And that helps me to understand the beginning, the origins of this theory. Yeah. Because otherwise, if you read some of these books, I think it's, you just let, a function is a modular form of this weight if it satisfies these conditions. And I wonder, well, why did anyone ever write this down?
Right.
I mean, you can work with, you can get up to speed, but.
Yeah, I mean, Diamond and Sherman motivates it from the opposite way, where they say, like, you want to understand something like Fermat's last theorem, then you can use modular forms to do that.
Yeah, that's a very the other way.
But also, I think not a bad way to do it.
I love this history. I also like this book by Roy, Elliptic and Modular Functions from Gauss to Dedekind to Hecke.
No, I don't know that one either.
But it doesn't bring you to where you are in this very second half of the 20th century and onward view of these functions and what they have to do with representation theory,
right.
Automorphic representation. All right. But okay, back to this. Block. So I understand what is meant by the rank of an elliptic curve.
Right.
But you are dealing with a conjecture that relates the order of vanishing of an L function to something else, which I believe is meant to take the place of that in a more general way for some other kind of variety. Is that right?
For some other kinds of Galois representations, yes. So okay, elliptic curves also have Galois representations attached to them. This is called the Tate module. Essentially what you do is you look at the p powered torsion. So you look at okay, what are the points of order p on your elliptic curve? And if your elliptic curve is defined over Q, then like if all the coefficients of your equation defining the elliptic curve are rational, then the Galois group of Q acts on the p torsion points, permutes them in some way. And same is true for p squared torsion, p cubed torsion. And then there's this limiting process that builds you a p-adic thing out of that. And that's the Galois representation attached to the elliptic curve. And
these are the points over C.
These are the points over Q bar or C or whatever algebra. They're all going to be over Q bar, but you can think of them in C as well. Yeah.
Okay, because it makes sense to me why they should have the structure they have, over C.
Yeah, because it's a donut.
Yeah. Okay. So that's the Galois representation attached to an elliptic curve. But what is the object on the other side of this Bloch-Kato conjecture? What is
this is what's called the Selmer group. So for an elliptic curve, there are many ways actually you can define the Selmer group, and they're all such that they the dimension of this, it's really, you can view it as a vector space over the p-adic numbers. And they're all such that if you view it this way, then the dimension of that vector space should be the rank of the elliptic curve. And that's part of the Birch and Swinnerton-Dyer conjecture, essentially, is that whatever error there is in that statement is finite.
I see. I mean, I guess that has to be the case. This is some generalization of that thing.
Yeah, it's like if you take the elliptic curve, like the rational points on the elliptic curve, you view it as a group, and you tensor it up over Z to QP, where QP is the p-adic numbers. This is more or less what you get.
Wait, some of this algebra already, I never, they lost me at some group cohomology and.
No, don't worry about group cohomology. This is just the way you would define, the generalization of this group of rational points for arbitrary Galois representation like this.
But somehow, isn't it supposed to, it's supposed to measure somehow the failure of this Hasse principle? Is that?
Yeah, for elliptic curves, that is one interpretation of what the Selmer group and the Tate-Chafarevich group do.
Two different ones.
Yeah, so you have essentially the rational points on one side and the Tate-Chafarevich group on the other side, and in the middle lies the Selmer group. Selmer group connects these two outer things. Technically speaking, there's an exact sequence with the Selmer group in the middle, but okay. And the Tate-Chafarevich group is conjectured to be finite. That's not known in most cases. But it's like the error. The Tate-Chafarevich group is like the error for whatever this object is, the Selmer group, to capture all the information you want to know about the rational points on the elliptic curve. But the things I'm dealing with, like these Galois representations, they don't have rational points or anything. The next best thing is something like the Selmer group. They do have something like a Selmer group, or I mean, they do have a Selmer group, and that's what I'm looking at.
I see. I mean, maybe it's because I tried to look up and I found some paper of what the Bloch-Kato conjecture is, and I thought there was some kind of variety. There was some kind of algebraic geometric object on the other side of this thing. But you are able to talk about it.
Actually, it is a conjecture that there is always something. They always somehow arise from an algebraic geometric object in some way. Or at least the Galois representations that the Bloch-Kato conjecture aims to explain. There are other conjectures that say they always somehow come from geometry, but that's not what I'm actually interested in.
Okay. Then because let's throw that all aside.
Just throw the algebraic geometries aside for this conversation. Yeah.
Okay. Terrific. So really, what you're trying to do is, what were you trying to do in this paper?
Well, in this paper, I'm looking at. So I take a modular form and I take that Galois representation that's attached to it, and I do some operation on it called the symmetric cube. So I look at, the symmetric cube is just, let's put it this way. The Galois representation attached to a modular form is the Galois group acting on a two-dimensional vector space. And you can build out of this two-dimensional vector space another four-dimensional vector space on which there is still this Galois action, but it's built up in the symmetric cube way. And I want to study that Galois representation instead of the Galois representation attached to the modular form from the point of view of the Bloch-Kato conjecture.
But sorry, why do you want to do that?
Because the Galois representation attached to the modular form is already studied from the point of view of the Bloch-Kato conjecture by Skinner and Urban. And I haven't really even said what the Bloch-Kato conjecture is supposed to say yet. Maybe I should say that. Okay,
wait. So say that first, and then I'll ask you again about this symmetric cube.
Right. So the order of vanishing of this L function attached to a Galois representation. You can define a Galois representation using these Frobenius elements, like I was saying before. You can define an L function attached to it using Frobenius elements, like I had said. You just do some characteristic polynomial of the Frobenius, and then you plug in some like p to the minus s to it or something. Anyway, you build this analytic object that should control interesting properties about these Galois representations in some way, and you conjecture that they do control interesting features of these Galois representations, because in the cases that we've seen as mathematicians coming up to the 21st century, this has been the case. We've seen these patterns in smaller cases like the Galois representations attached to elliptic curves or modular forms and things like this. But anyway, so the order of vanishing of this L function at its central point should be how it should measure the size of this Selmer group attached to a Galois representation, which I don't really want to say what this Selmer group is, but it's some replacement for the rational points on an elliptic curve.
Yeah.
So this is the way in which it generalizes BSD, is that you have these two numbers that you can attach to your Galois representation, and they should be the same. Namely, the order of vanishing and the size of its Selmer group. And so the thing I did in this paper, if you just wanted to ask the same question about modular forms, this in particular contains the question about elliptic curves, right? This in particular contains, because for every by Wiles, because that every elliptic curve has a modular form attached to it, and these are all these objects end up being the same. The L functions end up being the same in all of this. So in particular, if you ask the Bloch-Kato conjecture for modular forms, then you're in particular asking it for elliptic curves, right? Does that make sense?
That's a special case.
It's a special case, yes.
So you mean BSD is a special case of this Bloch-Kato?
Exactly. For modular forms in particular, or for Galois representations attached to modular forms, really.
But so you are looking at what more? Are you looking at a larger class of what?
No, I'm looking at the same. I'm starting with the same modular forms, but then I'm taking the symmetric cube Galois representation. And there's a very good question as to why I would ever do that.
Yeah, that's what I was going to.
Right. So one way to motivate it is just, there are there are only so many operations you can do to this Galois representation to produce a new one. And they all come from these symmetric powers. So symmetric first power is just the same thing as the original Galois representation. And that was already studied by Eric Urban and Chris Skinner. And that was the same work that I do in this paper. It was done by them for just the usual modular Galois representations attached to modular forms. You can take symmetric second power, and it turns out this is one ingredient in the proof of Fermat's last theorem to understand the conjecture for this, by the way. So Weil sort of already looked at this Selmer group himself.
Well, I guess I was thinking, well, what is the relationship? You don't need modularity here because you're starting from
just starting from a modular. Yeah, from a modular form. I don't need an elliptic curve in the picture. In fact, I'm starting from a modular form of weight at least 4. So in fact, elliptic curves are excluded from my the statement of my theorem.
Okay.
But anyway, yeah. So you can then try to ask the question about the symmetric third power, and that's what I try to answer in this paper. That's not the reason I did this. The reason I did this is that I was really interested in the method of proof used by Skinner and Urban when they attacked this modular form case. And I wanted to see, what other situations could you apply that method?
Well, that is a fruitful, way of doing research.
Yeah, and in fact,
for sure.
That's what Eric suggested. He was like, well, he didn't suggest the symmetric cube. He actually suggested trying using the method on G2 and see if you can get anything out of it.
Well, there's a, so I can imagine, I know what it. I believe I know what it means. You have a representation, and what is it? It's symmetric cube or some other constructions made out of representations. And I can believe that there might be some decomposition of that symmetric cube
but they're actually, in the cases I studied, the symmetric cube is still irreducible.
Okay.
Yeah, it doesn't decompose, and that's why it's somehow more interesting in this case.
Okay.
It's a 4-dimensional thing that's still irreducible, and then you can study it.
Okay. I don't know where G2 is coming in.
Right. So that's a very good question. So let me say where it's coming in by drawing with my hands. So,
well, actually, but before, okay, I just want to know if what you are doing in the end is in any way similar to, like I feel like I got some sense of what if what you're doing is somehow analogous to a part of BSD, but in this other case, right? Is it analogous to the paper of Gross and Zagier, where they, there's the vanishing, and now I've constructed an object in this, they construct a point of non-zero height, or is this some?
No, it's not analogous to Gross and Zagier. It's analogous to Skinner and Urban, which is a different way to get at these rank 1 cases for modular forms. So there's Gross and Zagier, they have elliptic curves, and they have the rational points on the elliptic curves, and they're working with them, but there's no rational points on anything here.
I'm just asking if the point ultimately is, say, given the vanishing of an L function, you somehow construct something in the right hand side.
Exactly. That's exactly what I do. Yeah.
Okay, but it's not rational point, because you're not dealing with that. It's something attached to a Galois representation is what you construct.
Yeah.
That wasn't
an element in a group attached to a Galois representation in some way that would not be worth explaining at this level, I think.
I see. Okay.
But anyway, there's some object whose I mean, really the way I view this Selmer group is it's the object whose purpose is to predict that there should be some non-trivial element attached to the vanishing of the cell functions. Like somehow it's a little backwards, but this is what motivates me. There's some algebraic object that is supposed to measure the order of vanishing of this analytic thing.
Well, does it, can you say concretely how it relates to what you were talking about earlier about the splitting of primes, or, something about? Yes,
you can see a little. So there's a much bigger group called the first Galois cohomology of this representation. Don't mind what that is. Some bigger group. But it has the property, so this Galois cohomology is constructed out of, functions from the Galois group to the representation, or to the space of the representation. Co-cycles built out of, they're just some kinds of functions from the group to the representation. But anyway, you can restrict those functions to these Frobenius elements, or really to these decomposition groups, which are really looking at the local structure of the Galois group at various primes.
Mm-hmm.
And you want to demand that essentially these restrictions are as nice as possible in some way. That is the defining condition of the Selmer group. So it's really somehow you take this big global thing called the Galois cohomology of this representation, and you look at a subspace inside of that big global space of functions that are locally very nice. And so this somehow gets back to this whole, failure of the Hasse principle. Even like, really, it's you're.
Oh, we didn't say what that was, by the way.
Yeah. So the Hasse principle is a similar idea. You want to know that something is globally nice if it is locally nice at each prime. And so this is measuring the failure of that.
And that makes sense to me for something like the points on an elliptic curve, right? How much does it tell you that you could solve it, or not, how many solutions it had modulo each prime? How does it relate to the points on that curve over Q? But it's much more complicated on a thing like that than on a quadratic, I guess, where you. Yes. But what does it mean exactly for a Galois representation?
To be nice at a prime. It means that, the technical term is unramified. So it means that this Frobenius element determines the entire behavior of the Galois representation at that prime. No other interference from what's called the inertia group at that prime.
And is that what that knowledge of this Selmer group would tell you about which primes are unramified? What I'm just trying to get some kind of picture of exactly
it would be related to this ramification story, but it would not tell you specifically that a Galois representation was unramified at a prime or something. It would tell you I'm not even sure that much what it would tell you about the Galois representation, other than the fact that its L function should vanish to that order, right? So,
well, that's
I apologize that I can't really answer a very basic concrete question with the things that I'm doing here, but
it's perfectly fair.
I have to confess that's not why I care about them.
It's fair. In a format like first of all, I'm putting you on the spot, and second of all, you don't have a board to write stuff down. Just anything that I'm curious about, or I'm going to say, just in case you can help enlighten me, or.
Yeah, I mean, for me, it's just there's this supposed relation between these two things, and it's very mysterious why they should be related, and they seem to always be related, and so I want to know why. Right, it's just mathematical curiosity.
All right, well, also you prove it to be the case, then people will treat you really well. I think you're treat you like this Peter Schulze.
No, I don't think people will treat me like Peter Schultz. I don't deserve to be treated like Peter Schultz.
Well, we'll see. I
want from a mathematical point of view.
I want a theorem to my name, so you gotta get some respect somehow. But anyway, okay, so I sort of I feel like on the level I can understand, I sort of see the plan, at least of the general Bloch-Kato, and what I think you're trying to do. You want to show that are you actually showing the whole thing? Or are you showing?
I'm assuming I'm doing one way. Yeah, so I'm assuming the L function vanishes to odd order.
Mm-hmm.
Yeah. Then I can construct some non-trivial element in this Selmer group.
Okay, so it's an odd order that you can have at least one
yes.
thing. Okay. Okay.
And I guess that's the thing that I can't motivate to, from the point of view of just solving an elementary problem. I think that's not something I can do, but I can try to motivate.
It may be too long a story somewhere in there, in the definition of these crazy groups that I somehow never understood. It does say something about that representation and something of a more like a concrete number theory thing that a mathematician of the 19th century would have understood.
Maybe not even in the 19th century. I don't know. I mean, like I have number theorist friends who would legitimately ask me, why do you care about a Selmer group? And I think it's a legitimate question. Like it's why would you care about a Selmer group? And I think the best answer for me, at least, is just because it's this algebraic object that predicts the analytic order of vanishing of an L function.
Okay, well, I actually don't like that answer, because the two should have different definitions, and you want
they do have different definitions,
and different significances too. And it should be good that they're combined.
You know what? I agree with that. I agree with that. There should be. I should be more readily able to tell you what the significance of the Selmer group is, besides the fact that it predicts the order of vanishing of the L function. I agree. Yeah.
At least I understand.
Like Peter Sarnak once said that what good is a formula if you can't describe at least one side, right?
So. You should probably just describe both sides. The
formula is even better if you can only describe one side, right? Because then you can describe the other side because of it.
Okay. Let me.
Anyway,
because I do know what is the rank. For BSD, it does make. I know what is the rank of an elliptic curve, and it's a separate idea, the order of vanishing of some series. But okay, all of that is fine. You want to, so now I sort of see what you're trying to do. In 120 pages, you construct, you take as an assumption a certain L series vanishes to odd order, and you exhibit a non-trivial element of this thing.
Exactly.
Okay. What does G2 have to do with anything?
Right. This is exactly where G2 comes in.
Yeah.
So to get started, you need to start not on the Galois side of things, but you need to actually start with this modular form that you're given. And this is the whole automorphic part of the story. This word automorphic forms is where is going to come up here, because you need to go up to this G2 group, right? So a modular form is in some sense a GL2 object. So like the generally linear group with 2x2 matrices. You can view a modular form. There's a construction that lets you view a modular form as a function on GL2 of a certain ring called the Adels. And you need to view it there, because then this GL2 of the Adels will act on functions on itself, right? So if you have any group, the most natural thing to let the group act on is functions on itself, right? This is sort of the starting point of representation theory. So in other words, I'm introducing representation theory into the picture as a tool to study this modular form. And the way I'm doing that is by viewing a modular form as a function on a group.
Right.
I haven't told you why that's helpful yet, but
well, so okay, so maybe I understand the picture of trying to understand the representation theory of groups, and I remember I took a course just on SL2R. I was an undergraduate taught by Steve Zeldich.
Okay.
Wonderful course. Of course, so we are already skipping ahead to a very much a 20th century topic because you're talking about a non-compact group.
Right.
To start with, where its representation theory is much more complicated than the compact groups. But so you're and they don't have finite dimensional unitary representation. So you're trying to look at an infinite dimensional space on which these things act and decompose it. So L2 of functions on the group, and the group acts by translation, right? But so the map, I believe, you're starting with functions in the upper half plane, but those or forms. No, okay, functions in the upper half plane, which have transformation properties. So you're decomposing, the space L2 of how many times? What do I? You can, that group acts transitively on that upper half plane, right? And when you modify something, you look at where a certain group element sends like I or something, and so there's some identification of the function on the group and on these spaces.
Exactly. Yeah.
Okay. Well, I understand at least the goal of trying to say what are the irreducible unitary representations, and how does this the whole space decompose? I've now it's so long in the past, I forget the story of the answer. But I know these spaces of modular forms are part of it.
Exactly.
But if that's still not the automorphic part, somehow you now also bringing in what it has to do with every prime, because I just know this real.
Well, I mean, it is the automorphic part of it if you demand that you're just looking at functions that are invariant by GL2 of the rational numbers. Okay, so if you're in the Adels, you think of GL2 of Q, but if you're like on the upper half plane, you think of like SL2 of Z or something. You demand that you're invariant by SL2 of Z, or at least transform in some way under SL2 of Z. This is the automorphic part of it. Automorphic means that it stays the same when you translate it by these elements. So it has the same shape.
So there's no further restriction that has to do with, I don't know. I have a lot of trouble thinking, wrapping my head around the Adels and maybe it's notation, but I
mean, the way the primes come in is just that the Adels are constructed from each prime, but the modular forms are there whether or not you've put them on the Adel group. But you can use the fact that they are on this Adel group to study the modular forms. And this is one way you can see Hecke operators as like convolution operators on spaces of functions on the group GL2 of A. But anyway.
Yeah, that's not a way I'm used to thinking of these
and it's a much more, automorphic way to think about it. Automorphic in the sense of, automorphic forms in general. But
Okay. So what I was asking you about G2 and this modular form.
I started talking about GL2, right?
Yeah.
Well, GL2 sits inside of G2 as a so I don't know if I should throw out this term, but as a Levy subgroup.
And now you're using terms.
Anyway.
I don't know. I didn't go this far into the lead theory, but
that's okay.
Can you just say what is G2? Where is it?
Yeah, G2, that's a very good question. the way I think about it is through this abstract classification of Lie groups via its root system. But usually that's the way I think about it. Some people think about it as, okay, you let some weird construction where you let where you look at all the automorphisms of split octonions that are traceless. You construct some group this way. It's a group with this nice property called that it's semi-simple. It's actually simple. That is classified, and all such groups are classified, and this is one of those ones that doesn't fit into the usual scheme of classification.
So this was something that was it first seen for the first time when Killing had his paper classifying these groups or their Lie algebras?
I think so. I think this was like, I think it was Killing who saw this for the first time, if I remember correctly. It might be someone else. I'm not sure. Well, but anyway, it was an early 1900s kind of classification of Lie algebra.
I think this is in the 1880s. I love this result, and okay. Some people have called his paper one of the greatest math papers of all time, because okay. he answered this question, sort of just like classifying the Platonic solids. In ancient times, people figured out the numerical criterion so that you could have a solid figure, all of whose faces were regular polygons and the same number met at every vertex. And that's probably how, I don't know if they had discovered the dodecahedron or icosahedron prior to that, but numerically, it worked out, they were allowed, and then people were able to construct them. And very similarly, Killing was trying to answer this question of, you could say almost like, what are the basic building blocks of continuous symmetry groups? Right. The rotation groups. If you have to restrict to compact objects, not non-compact, and you say that they're simple, so they're not composed of other things. And I actually I'm preparing to do one of my videos on this. I think this, at least an outline, you can explain what he did. Where do these things come from? And you can see that just the fact that it has to be a compact, simple group, but it's also a manifold, eventually tells you with enough numerical criteria that here there's these restrictions. And in fact, there are 4 infinite families that are basically all types of rotations. And then there just were 5 extra ones, 5 ones that occur in just only a certain dimension. There's only, and they, and maybe a good reason why is not, it's hard to explain. This is where you get this thing called like E8 that probably some people have heard about. Maybe, Eric Weinstein was talking about it, and there's this guy, Garrett Lisi. A lot of people study this E8, which is the biggest exceptional group, but also there's this thing G2.
It's the smallest exceptional group, actually. Yeah.
Right. Which, at least in his classification, so as far, I think I mentioned this, but as far as I've ever gone in my study of this thing, like I know here's a root system that is allowed by this thing that didn't fall into it's not doesn't belong to one of the rotations of Rn, or, it's not SUN or whatever. But it's something else. It's allowed. You could construct the Lie algebra based on this root system. But I've never thought about it as a group, and I don't know where but to see that it shows up in some important math is very interesting to me. And
it's a weird little thing that you can access the symmetric cube through G2 in some way.
Yeah. So can you help explain to me it just in any way, where do you see why is G2 appearing?
Right. So I should have a picture here. Oh, I know exactly where to get a picture. Hold on. Okay. I have a picture. Okay, I have this coffee mug. It has a drawing I made of G2 on this side of it, but then it also has the root lattice of it on this side.
See, that picture I know. That picture I could actually explain.
Yes.
The other one, I have no idea what that is.
Well, because I drew it just for fun, but anyway, it's supposed to be a picture of G2 because it's a two-dimensional torus with 12 unipotent directions coming out of it. It's like an artist's rendition somehow of G2 or something. But anyway, that's not the point here. The point is this side.
Well,
So
see, it has such a nice picture here, but G2 is like a 14-dimensional object,
exactly.
right?
So this is like the torus in the middle here. This is like some two-dimensional point, and then there are 12 other dimensions coming out of it. So let me show you why this four-dimensional symmetric cube shows up here. So like I said, you start with this modular form and you view it as a function on GL2 of some ring, right? So you're starting on GL2 essentially. GL2 is a four-dimensional group, and actually you can see it right here in this one dimension plus this two-dimensional point. So why can you see this? So these points that are pointing out should be like they should be like upper triangular or lower triangular matrices. They're unipotent is the technical term. Mm-hmm. And this thing in the middle is like the diagonal matrices.
Yes, this plays a role in this classification. Okay, exactly. I think I know what you're talking about here when you talk about one direction of these roots.
Right.
The root and its minus it and the ones in the center.
So now how does this GL2 in the middle act on everything else? Well, what it does is it takes one of these directions and then takes something and translates by it. So you look up here, you see this four-dimensional line up here getting translated by this GL2 in the middle. That is the symmetric cube seen inside of G2. The symmetric cube representation of GL2 seen inside of G2 is this line up here getting translated back and forth by this GL2 in the middle.
I have to think. So you started thinking about GL2 and its symmetric cube, and ended up with.
I really started thinking about just this whole group G2 and seeing what it could say via the Skinner-Urban method about presumably a modular form, because you can only see GL2 as smaller things inside of G2, but. So presumably, since there was a GL2 inside of G2, a modular form was going to show up in some way, and you want to see how it shows up. And this is telling you the symmetric cube is showing up more or less.
Oh, I'm not okay. But I was hoping you could tell me. All right. So here's my confusion. I want to see without knowing to look at G2 from the start that it appeared somehow in the question you were trying to answer.
Right. That's not how I came to this question, but I can still try to explain. So if you have this modular form, it's some function on this group GL2. What you can do is there's this operation in representation theory called induction, where if you have a representation of a small group, you can construct a representation of a big group by looking at functions on the big group satisfying some symmetries under the small group. That's exactly what you do. You induce up from this GL2 inside of G2 to G2. And when you do that, you sort of see the whole picture of G2 and very vaguely, you see the whole picture of G2 getting acted on by this GL2 in that way. And so you see the symmetric cube.
Okay, I guess
that's very vaguely where the G2 shows up in the picture. If you want to study the symmetric cube of a modular form or of a Galois representation attached to a modular form.
So I mean, could you do the same thing? Could you ever do the same thing for like E8 or something, or any of these?
Well, E8 doesn't sit as a smaller group instead of any bigger groups because it's the only. I mean, not as a Levy subgroup, to throw that technical term again. E8 is not the Levy subgroup of, so, you have to use some properties of this subgroup, the GL2 instead of G2. And E8, it does not have those properties sitting inside of any other group because it's the biggest exceptional group. But you could do it for like, I mean, Skinner and Urban originally did it for GL2 inside of SP4, or really GSP4, but SP4, you know, C2 instead of C2. It's going from A1 to C2 in the classification, right? Here it's going from A1 to G2 in my work.
Okay, I just, so I guess I don't know enough about this, some of this Lie theory to say which groups, but presumably, I don't know.
I mean, there's various pieces of numerology that will let you know whether or not this method should work. And since I haven't told you what this Skinner-Urban method is, it's very hard to say what those numerology pieces should be. But
Sure.
GL2 inside of G2 did satisfy this numerology. Once I knew what this numerology was, I saw that GL2 inside of G2 satisfied it, and knew that I could maybe make this work with the symmetric cube.
But potentially you could have used something else. Is that
not to see the symmetric cube? See maybe other things from GL2, but like Skinner and Urban just saw the standard representation inside of SP4.
I just got, because I'm just trying to wonder, why is G2 forced upon you, or if it is?
I don't know. Well, I mean, from the point of view of just using this method, it turns out that it is forced upon you just because you try to classify all the situations in which this method could work based on this numerology I haven't told you, and you rule out a bunch of different cases, and you see that G2 is the only one left that could see the symmetric cube. So like G2 is the only group in its root lattice that has a root string of length 4, and that's somehow that 4 is the important thing.
Okay, interesting. I didn't know where it could have come up, and I mean, I see that I guess I see that makes sense. This string of 4, but I don't know
Yeah, I mean, I haven't told you anything precise about why G2 shows up. So
I can imagine how you use you use that root lattice to understand the representations of G2 and the properties associated with it. Okay, maybe now the question I want to ask, which is, well, what I always want my guests to speak to in some way is the tools that they use, the techniques. How do you actually do something? And of course, you don't have a blackboard, and this is the most technical part. So it's hard to actually give the proof, which you can't give it here. But I wonder if you can give some kind of flavor of what it is that you use. How do you actually get at new information? It can't just be putting together all the structures that you have. Where's the
you really have to say something about the structures once you've put them together.
Yeah. So maybe it just even vaguely, and even if it doesn't connect to the rest of the story, can you tell me how do you do it?
Yeah. So I think of it as it sort of goes in 3 steps, and I can sort of draw a picture in the air, show you what those steps are. So the first step is to do this passage from GL2 to G2. It's you start on something small and you go up to something big, right? You start here on GL2, you go up to G2, that's starting something small, going up to something a little bigger. And why would you do that? Well, you haven't really gained much information yet by doing that, because all you did was you induced your modular form on GL2 to something on G2. You didn't really get any extra information this way, because you haven't really made anything new out of it. Just looking at some representation of G2 now that is coming from GL2 in some way. Now, how do you get something new out of that? This is where the p-adic theory comes in. Now and this is where the deformation sort of thing comes in. So there's you show, and this is not trivial, but you show by doing a particular computation that G2, this representation of G2 actually lies in a bigger family of representations. Whoa, that was interesting. The Zoom said I'm about to raise my hand when I did this.
Oh,
the Zoom did like some weird thing. Okay, anyway. So anyway, you show that this representation of G2 you have can be deformed in some family of representations of G2. And it's the members of this family that are less trivial, more genuine to G2 than this thing I took from GL2. And so when I do that, now I have some family. And this is all happening on, well, what I would call the automorphic side of things. So it's all happening on the side of automorphic forms. You're really doing, you're looking at representations of these groups. And as I said, there's this thing called the Langlands correspondence that lets you pass from, if you know it, it lets you pass from this automorphic side to Galois representations. So you start on GL2, you go to G2, that's the first step. The second step is to deform in this family.
I'm going to ask a little bit about that.
Go for that.
But continue with your...
Sure. So you deform this family, yeah. And then the third step is to go to the Galois side. That's doing it again, the raise your hand thing. You go to the Galois side, and you have some family of Galois representations now that are not into GL2 or anything, they're actually into G2. G2 valued in the p-adic numbers. So you have some family of Galois representations, and you construct in that somehow your Selmer element in this family. And the way you do that is it's this. I should just say a word about it. It's called this lattice construction. It's a very souped up version of, if anybody's ever heard of it, the Ribot's proof of the converse to Herbern's theorem. But anyway, some construction on the Galois side gives you this Selmer group element.
But this is a lattice like I would normally understand a lattice.
Probably not. No,
this isn't
it's like a lattice as
an integer, the integer linear combinations of some vectors.
It's more like the p-adic integer linear combinations of. So it's a p-adic thing. So it's like ZP sitting inside of QP. This is what I would mean by lattice. It's a lattice in that sense, instead of Z sitting inside of Q or R or something.
Okay, that is harder for me to wrap my head around.
That's okay.
But what is it that you have to do?
Yes.
Where's the hardest step in this whole thing?
The hardest step. The hardest step probably really is, now that I'm thinking about it, it's probably really in the work that I'm using that shows that there's this p-adic deformation on the automorphic side. So this, I mean, if you really want to go back, all the way and say what the hardest step is from not just my work, but the work that I use, it's probably that. But that's probably not the answer you're looking for.
Well, that's not the answer you want to give either. You're saying that
that's not the answer I want to give either.
Other people did the hard work, and you.
Yeah. So
you sure you did something?
There are. I mean, it's in showing that there's a new numerical criterion that lets you know when you can be deformed in this p-adic family, and that's a hard computation you have to do, looking inside of this whole space of automorphic forms and things like this. This is a hard step.
So okay, I mean, when you say deformation, because I think I've heard before that somehow the deformation theory is, by the way, it's been what I've been told is like somehow the key. It has to do with the key steps that are hard and I don't understand, even in the proof of modularity.
But this is not deformation theory in the sense of like algebraic geometry would call deformation theory. This is something.
Yeah, I know this is something else, because otherwise, it's like I understand how to take a derivative. That's one idea, but you're talking about
I'm talking
things that lie over another thing by congruence.
Exactly. This is a congruent thing. They're p-adically deforming.
Yeah. So the central issue has to do with existence of modular forms that satisfy certain congruences. Is that
exactly
right?
Except on G2 instead of GL2. Yes.
Yeah, and I have no idea what the reason that's so confusing to me, because I understand the connection between, even not for G, but the SL2R and transformations of the upper half plane, where these things live, and the subgroups of the congruent subgroups of SL2R. Mm-hmm. I know nothing about G2 and what it has to do with that.
But it's not. When you say p-adic deformation, even for modular forms, you don't necessarily mean anything about the congruent subgroups of SL2R. You mean what one means is congruences between the Fourier coefficients of the modular form.
Yeah, right. Okay, so ignore G2 for the moment. Yeah. So I gather that somehow the whole business has to do with, is it like showing the existence of certain modular forms that satisfy congruences, or showing that, given that certain modular forms exist, showing that they satisfy these congruences, or how does it go?
Yeah, more the latter. So, and then there's the question of how would you show that these things exist? Okay, is that what you want?
Or how do you show that the congruences exist, or
that there are modular forms congruent to your given modular form?
And is that where the work goes? Because it will satisfy.
That's what I want to say, except that it's not my work. It's my advisor's work that does that. My work is in checking that I satisfied the hypotheses of my advisor's theorem. At least on the automorphic side, that's where the work goes. On the Galois side, there's a completely different step that needs to be taken, but there's a lot of work to be done there too.
But is that where how do you do a thing like that? Can you give me any sense of what sort of tools are
right? So one way modular forms appear in all of this theory is they appear in just the usual singular cohomology of the modular curve. Some way. This is called
I understand this through the idea of taking there's like the what would it be? Because they're differential forms, they represent classes in cohomology. Yeah. I guess
that's one way to see it, and then to pass from de Rham cohomology to Betti cohomology. That's one way to see it. But there are other ways you can approach it without saying de Rham, more or less. It's basically the same. So you might as well just say de Rham. But yeah, okay. Anyways, but what's interesting about seeing modular forms in cohomology is that you could ask cohomology with what coefficients? These cohomology theories come with a coefficient that you select. The coefficients could be complex numbers, they could be real numbers, they could even be, you just take the cohomology with integer coefficients. And the fact that they appear in the cohomology with integer coefficients lets you get some handle on, modding these integer coefficients out by p and so on and so forth.
Okay, these different coefficients. This is another place where I am not. Things begin to lose me.
Yeah, it's just you have to pass to algebraic topology from differential geometry. Yeah,
I see, but that tells you that you can do so. I just what am I looking for here? I'm just looking for some kind of isolating the technique of either showing congruences or that there's a certain object that shows that has these congruences, and what work goes into that. It would please me very much to know how those sorts of things are done. If that's somehow the key step, the existence of those objects and satisfying a bunch of equations.
But I mean, do you want to know how this is done in general, or how this is checked that it can be done in my paper?
Anything you want to tell me? I'm not going to check your paper for whether it's
No, that's not what I mean. But, yeah. So I mean, my advisor has a general theorem in his paper on eigenvarieties that says if you can find your modular form or your automorphic form in cohomology in a particular way, there's some numerical criterion that needs to be satisfied. So multiplicity, non-zero multiplicity is what it's called. Then it actually lies in one of these p-adic families that is constructed via this cohomology. So you construct the family via this cohomology, and now you need to check that your modular form is part of this family, or your G2 modular form is part of this family.
Is eigenvariety?
Those are two different things.
Is this what is an eigenvariety? Is it somehow an eigenvariety of the Hecke operators? Is that
it derives it's a variety it's a variety in a loose sense that parameterizes eigenforms. It's just called eigenvariety because its the objects on it are eigenforms. And it's a p-adic variety. So that's where you see the congruences. It's really like a p-adic shape whose points are eigenforms. And
okay,
two things are close on this shape, then congruent modulo a high power of p. But how do you construct it? That's I think what you want to know.
Oh, that's where the work goes. Because I can imagine. Yeah, you define an object where the closeness is measured by this thing.
To know that there's two things: constructing this object and then knowing that my G2 automorphic form lies on this object. So
yeah, that's a solution to an equation. That's the kind of thing. Yeah, where I can imagine you need to do work or measuring closeness, whichever.
Yeah, so constructing this object is some work that my advisor did, and knowing that my G2 automorphic form lies on this object is the work that I did. And so to know that my automorphic form, a G2 thing, lies on this object called the eigenvariety, you need to essentially study very closely its appearance in cohomology. So you need to study where it appears in cohomology with what coefficients. And coefficients, I mean, not even in the sense of like, I always mean like maybe C coefficients here, but you can also take coefficients in certain C local systems, okay, whatever. There are other coefficient systems you can take, and you need to examine those too. Somehow some linear combination of all of this gives you, if it comes out to be non-zero, then you know you're on this eigenvariety. So it's in computing this multiplicity, as it's called.
Okay, I have to say I'm a bit lost, and I knew that I would be. I just is there a reference for this this deformation theory, or is it all just in the papers still? And
well, it depends on what you mean by deformation theory, because I'm using it in a sense that's different from what most people would use it. This is more about p-adic deformations of automorphic forms or something. This is different than like deformation theory, as in like Schlesinger's criterion or something. Yeah. I
don't know what that is either, but isn't it the same as what happens in this? What Wiles needed, like he started with.
It's a little different. It's a little different. The stuff that I'm using is not the same as what Wiles using. That's much more what algebraic geometer would call deformation theory.
Oh, and yours is different.
Mine is somehow more related to just the special case of automorphic forms, like eigenvarieties and things like this. It's different, but I
you
mean,
see why I'm. Do you see my
feel free to ask me
frustration?
questions about
Well,
either.
I just mean I get lost when people start defining more and more objects.
Yeah.
I feel like there's got to be an equation that you have to solve at some point, and you need to solve, and you just solve it concretely, or.
So
that's why
I don't really know how to find that equation on the automorphic side. I know how to find that equation on the Galois step, more or less. There are different things that go into different steps, and on the Galois side of things, I know how to tell you where that equation is. On the automorphic side, I thought about it because I knew you were going to ask me this question. I don't know exactly where it comes up. Like where is the inequality or the equation that ends up solving the problem? The closest I can come up with is you compute this multiplicity, which is a number, and you compute it to be non-zero. But doing that isn't really solving an equation. It's more finding every instance of this automorphic form in cohomology, and that's a little different. So I don't really know where it is on this p-adic side of, or the automorphic side of things. But
I wonder, am I even asking a sensible question? I just this is part of the puzzle for me, that I love to know how this sort of thing is done, and I don't want to learn about too much algebra to do it either.
You can't discount the value of commutative algebra. Like in Wiles's proof, you can't discount the value of commutative algebra there either, though. Like that, of course, the key to Wiles's theorem was proving an inequality in section 3 of his paper, but upgrading that inequality to an equality was also very important. That's commutative algebra. You can't discount the value of commutative algebra here.
And this is all about these rings of Hecke operators, right?
Yeah, you mean Wiles's thing. Yeah, this was about, well, it was about two kinds of rings. It was about these rings of Hecke operators. It was also about these deformation rings that are attached to these deformations that you seem very curious about.
Yeah.
I want to show that they're the same. They're isomorphic.
Yeah.
That's part of commutative algebra, essentially, after checking an inequality.
All right,
anyway,
all right.
That's a little sidetrack.
If you could tell me, I don't know, a paper or a book where I could
learn about deformation.
Because I guess I get very lost in that volume.
This is definitely not my specialty, so I'm not sure I can give you a good reference here. I mean, there's always like the kind of deformation theory that's used in Wiles's proof well, I mean, it has nothing to do with my work, but it was pioneered by Mazur. So Mazur probably has some writings he's done about it that are probably pretty good. Search Galois deformation theory, Mazur. I'm sure you'll find something. But,
okay,
I don't know of a good reference for that deformation theory.
You see why I'm not in this field. Once you start, there's too much notation, too much H0 and pick, and too many things, and I get very confused. I like things concrete. If you show me an equation that you're solving, it makes a lot more sense to me.
I mean, I think of representations as concrete objects too. It's not just equations.
Yes. I'm okay with that. But why am I okay? I'm asking perhaps a silly question of something that's outside of my domain of expertise, and now I can't seem to follow anymore. I've filled up my head here. Can you say, so what is do you have a plan? Where are you going with this path? Are you going to prove this Bloch-Kato conjecture?
No, I mean, that's too hard. Because then, just proving, that's way too much. But I do plan to tackle other cases of it. So right now I'm working on a project where which sort of thinks about the other direction, but uses the methods that I use more or less in this work, plus some upgrades. So there's another class of Galois representations that you could try to talk about the Bloch-Kato conjecture for. And the Bloch-Kato conjecture for this particular kind of Galois representation actually predicts that the Selmer group should be 0. And I want to try to show that for this particular class of Galois representations. And I want to use, even though it's the opposite direction, I know how to use the methods in the methods that I know to try to do it.
Well, that's smart. Let me ask you a different question. Maybe this is silly. Why go after this generalization of BSD while BSD is still unproven, and it's there's $1 million prize that on its own.
Well, maybe some people would like to answer, because it could give you more insight to BSD. Would it though? That's my. I am quite positive that eventually this should give you, expanding your horizons to this more general case should definitely allow for more methods to come in and help tackle these smaller problems or these special cases.
That would be good. Problem. Yeah. But you see, in my perspective, that would be the judge. That would be how you judge whether this was a good project. I have heard a lot of talks where someone mentions a very nice concrete problem, but then they say, okay, now I'm going to study it. The problem is unsolved. Well, this is just one small part of this much bigger thing that's that I want to study. And then they start talking about that thing and how far they can get there. But if they can never use that to get at the original thing, right? And I'm skeptical about why they. So here's a good example. So in BSD, you mentioned that nothing really is known outside of rank 0 or 1, right? But, I don't know that nothing is, but if that's true. Well, okay, so there's sort of an exception to this, and this is the rank 2 case in some special cases. So if you want to study even order vanishing of the L function, so if it vanishes to even order, then it is my understanding that Skinner and Urban more or less know how to do this using these methods that appear in for example, their work and the work that I've done that's based on that work. And you have to go, you have to sort of expand your horizons to this automorphic world to actually get at this. But do they do like they can actually construct 2 independent points? Yes. Of infinite? That okay. I would love to see that if only I could understand it. Two independent elements of the Selmer group, but that's essentially the same thing up to scaling. And but that would but in the elliptic curve case, that is yeah. The only thing I'm unsure is whether they've gotten all the way back to the elliptic curve case, because this is somehow a very irregular case in a technical sense that that makes it troublesome. But I believe they can do that. Okay. Let me not say anything for sure, but I'm fairly certain that this is possible. What about in this context? Is it clear, for elliptic curves, by the way, I think it's still unknown whether there exists elliptic curves of arbitrarily large rank. Right. Yeah. Right. And some people expect that there aren't, right? This is also a thing. Right. And so at the same time, I think nothing's on the other side. Are there modular forms whose L series vanish to arbitrarily large order? Oh, to arbitrary? Yeah, I don't know if that's known or not. I mean, probably it's not known. And is anything known about these Selmer groups in this analogously? About how large they could be?
so I mean, right? I don't think this particular question is known. I think people. I would doubt that people know the answers to this question. What people might conjecture about this question is a different story, and of course, that's also debated at this point with like this arithmetic statistics stuff that is going on these days. So
yeah, well, I've heard, yeah, like about half are rank 0 and half are rank 1, and the rest are exceptional somehow, and yet that still doesn't answer this question.
Right.
And I don't know whether it'd be easy. Is it somehow easier to construct something with a curve with large rank, or is it easier to try to find a modular form whose L series vanishes to very high order? I actually don't know, and
right.
I don't know how this looks or what that would mean on the Galois representation side.
Right. Well, I mean, it would mean that the Selmer group has a very large dimension. But
yeah, but and can you say what would that tell you about the Galois representation or the study of the absolute Galois group of Q?
Yeah, no, I don't think I have an excellent answer for this question at all. I apologize for that. I should have a better answer for that question, but I don't.
Just a curiosity. I mean, there are some people who want to study, like the inverse Galois problem. Does this have anything with this?
No, I don't know that somehow this area is a little bit separate. I'm not entirely sure about that. But I mean, maybe, but I don't know.
What I want to tell you, I'm working in this field of homomorphic encryption. Are you at all familiar?
No. Homomorphic encryption? What does that mean?
It means that the operation of encryption is okay. Now it's going to take me a little bit to get to how this relates to modular forms, which is what I actually want to talk about. But there is this one miracle technology now, and this is maybe why I haven't had a podcast for a while, because I'm building up this company to do this new form of encryption, where the whole point is that the operation of encryption acts something like a homomorphism, so that when you act on encrypted data, could be numerical data with operations like additions and multiplications, you're acting on an encrypted thing, which is like noise. But when you decrypt, you get what you would have gotten had you operated on the unencrypted thing. And what makes that so wonderful is that now you can do outsourced computation and privacy preserving machine learning and all kinds of things. You could give your data to someone else. You don't want to expose your data. They don't want to expose their model, but now you can give it to them encrypted. They can act on it, give you something, you decrypted, and you learn something, and no one had to expose anything. But I just want to say the security of this scheme is based on something like a lattice problem, a problem of finding like the closest vector in a lattice, or the shortest vector in a lattice. And I was long thinking about if you could, if only you could break, then I wouldn't have a job. But the strategy, how could you find in a lattice, which is this span of a bunch of vectors, you're given some basis, but you don't know, in a very high dimensional space, it's very hard to find which is the shortest vector, or given a point, what vector in that lattice is closest to it. This turns out to be this, it takes exponentially long, and that's what accounts for the security of this scheme. But, you could take, I guess I was thinking, why don't you construct the theta function of this lattice? Mm-hmm. You're given the lattice with in some way, and the theta function of this lattice will be some modular form. And so it has an expansion, and so you could read off the first non-zero coefficient will be, will correspond to the shortest vector. and there's some other way to make sense of the closest vector problem. But does that make sense what I'm saying?
Why does the first non-vanishing?
Because you have a sum of like a series q to the, and these x squared, or the size of a vector.
Oh, I see what you're saying.
And
right. Okay, fine.
So where the sum is over all vectors in the lattice, but because that thing is a modular form for some congruent subgroup and some weight, it lives somewhere, and it also, you could rearrange those terms where, of course, the first non-zero coefficient corresponds to the shortest vectors in that lattice. So how can you get a hold of that thing? Somehow using the theory of modular forms.
Right.
Well, I guess I learned someone, just telling the story. Someone beat me to this. This has been studied. There was a paper from a few years ago, the modular form approach to solving lattice problems by Yuan, Shuiyang, and Rongxin. I think only from like 2014 or I don't know. Sometimes I don't see the dates, but here's the problem. Like it all that does work, but here is the problem. So it's a modular form, and now you need to. It lives in a space where you could say at the outset, what dimension the space of modular forms, and you could give a basis of those. And there's a couple of things you could do. I mean, you could find its Fourier coefficients by integrating it, or you could find it by taking the inner product with that basis. But there's your problem, because you need to know the values of that thing, and you don't know the shortest vector. So you have
the values of which thing?
The values of that theta function. You need to sample. You need to actually sample it. You know what it is abstractly.
Yeah. Right. Yeah.
But you don't know its Fourier coefficients, and so it's supposed. Okay, so if you wanted to integrate it, you'd need to know enough of its values in order to get something on its. You know it has integral coefficients, or you know that it has some nice, or it's easier to take the. Turns out to be better to take its inner product with the basis that you already have, and you can do things in an approximate way because it has to have an integer coefficient. So as long as you're close enough, you can get it. But that means you have to sample this thing in some way. You have to use this discrete Gaussian sampling, and that's what makes it take exponential time. So nothing has been broken. I don't know if you knew. I don't know if you can use anything more about these modular forms.
Yeah, I mean, to say that of course, you can give a basis of eigenforms, but I don't think that will help you. I think that's just somehow too far. I mean, the study of eigenforms is too far from this kind of thing. I mean, you can take that basis, but I don't think it's gonna tell you very much.
I mean, that probably is what you do, but you just need to know what are its coefficients in that basis, and that's
right. And that's already
That's why this doesn't work. I guess that's fortunate for this whole
yes.
It's very different for me. In cryptography, you want the problem to be hard and unsolvable.
Right.
Solvable problems. All right, that's my story. That's how I connect at least a little bit, because I'm not in this area of that you're talking about, but
no, but that's cool.
A little bit.
Cool.
And I'm hoping that, so I'm hoping to do that episode of what little I know of the 19th century theory of this classification of groups. The 20th century theory is more advanced, and I probably won't say anything about that. But I do think it's a shame that a lot of students don't see that. I've come to think that an undergraduate education should pretty much hit a lot of the 19th century mathematics, and like graduate school is for like 20th century mathematics. Maybe you specialize in one thing and see what people did in the 20th century but very few people, I think, see that that classification theorem, which is physics.
I think the people who are closer to physics end up seeing it. Yeah, but it's a very, very, very nice way of thinking about the whole theory, actually.
Okay, I mean, you did a very admirable job of explaining what it is that you do. Is there anything else you want to plug, or I don't know? I'm not a talk show host where my guest has a a movie out. You have a paper out.
Right, I have a paper out. I just need it to be published, and I don't know how much a podcast can help with getting it published, but we'll see.
Yeah, well, you want people to know. Mathematicians, especially who are young, you have to sell. You actually have to sell your work somehow.
Yeah, that's true. That's true. Yeah. So, there's nothing much else I can say. I basically said everything I can.
Okay. Well, thanks so much for doing this.
Thank you for having me on.